Welcome back everybody. In this chapter, we're stepping into one of the most important topics in networking, IP connectivity and routing. Routers are essential network devices that connect different IP networks together. They intelligently forward packets toward their destination, allowing devices on separate networks and locations to communicate without manual intervention. By analyzing routing information, routers automatically determine the best path for traffic to take across a network. In this chapter, you'll learn how routing decisions are made and how networks are configured to ensure reliable communication. We'll start with static routing, exploring the different types of static routes and when they are best used. You'll then move on to dynamic routing, where routing protocols automatically discover and maintain routes to remote networks. Finally, we'll introduce First Hop Redundancy, explaining how networks maintain gateway availability even if a router fails. The topics covered in this chapter: understanding static routing, configuring static routes, understanding dynamic routing, configuring dynamic routing protocols, and understanding first hop redundancy. Unlike switches, Cisco routers do not forward traffic automatically. Each router interface must be configured with an IP address, and each interface must belong to a unique IP network. Until this is done, a newly unboxed Cisco iOS router does nothing. It has no routing information and no idea where to send traffic. When configured an IP address on a router interface, the router automatically adds two routes to its routing table: the directly connected network and a local route for the interface IP. In this topology, there are three networks. After configuring IP addresses on R1's Gigabit Ethernet 0/0 and Gigabit Ethernet /01 interfaces, R1 only knows about the networks that are directly connected to it. It does not automatically learn about the 192.168.3.0/24 network. As a result, if PC1 tries to reach 192.168.3.0/24, R1 will return a destination unreachable message. By default, routers only know about directly connected networks. Everything else is considered a remote network. This is where static routing comes in. A static route manually tells a router how to reach a remote network. Looking at the topology, traffic destined for the 192.168.3.0/24 network must be sent from R1 to R2, specifically to R2's 192.168.2.1 interface. In simple terms, traffic destined for 192.168.3.0 should be forwarded to 192.168.2.1. The static route configured on R1 would be 192.168.3.0, subnet mask 255.255.255.0, 192.168.2.1. When configuring a static route, always follow this order: destination network, subnet mask, and next hop IP address. Instead of using a hop IP address, you can also specify the exit interface. For example, Gigabit Ethernet 0/1. Remember, routing must work both ways, so R2 will also need a route back to the 192.168.1.0/24 network. Static routing is simple and predictable, but it also has its limitations. In the next section, we'll explore the advantages and disadvantages of using static routes in enterprise networks. As a network grows, the number of required static routes also increases. Any change to the network, such as adding, removing, or modifying a subnet, requires a network engineer to manually update static routes on each affected device. While static routing works well for small and simple networks, it quickly becomes difficult to manage in large enterprise environments with many subnets and remote sites. That said, static routing still has important advantages. Because static routes are manually configured, they provide greater control and improved security compared to dynamic routing protocols. Dynamic protocols automatically update routing tables, which introduces the risk of malicious or misconfigured route advertisements. With static routing, routes cannot change unless an administrator explicitly modifies them. Static routing is also computationally efficient. Dynamic routing protocols rely on algorithms and metrics to calculate the best path. Static routing requires no such calculations. The router simply matches the destination in the routing table and forwards the packet. Once the best match is found, the search stops. Another benefit is predictability. Static routes follow a fixed path, making the next hop easier to anticipate. In contrast, dynamic routing protocols may change paths when the network topology changes, which can alter the next hop based on protocol decisions. The best use cases for static routing to force traffic to use a specific, unchanging path, to configure a default route for internet-bound traffic, and to create a backup route in case the primary path fails. In the following sections, we'll explore the different types of static routes and learn how to configure them on Cisco IOS routers. Network routes are the most common type of static route. They tell a router how to reach an entire remote network. Here's an IPv4 syntax. Here's an IPv6 syntax. These routes are typically used to reach networks that are not directly connected. Next hop static routes specify the IP address of the next router that should receive the packet. Here's an IPv4 example and an IPv6 example. Why use them? The route always points to a fixed IP address, predictable and easy to troubleshoot, and does not change unless manually modified. Instead of specifying the next hop IP address, these routes specify the exit interface, an IPv4 example, and an IPv6 example. The key idea, the router simply forwards the packet out the specified interface without caring which device receives it next. Fully specified routes include both the exit interface and the next hop address. Here's an IPv4 example. IPv6 example uses linked local address. And why use them? Maximum control required in some IPv6 scenarios and eliminates ambiguity in routing decisions. A default route is used when no other route matches the destination. It is most commonly used to send traffic to the internet. The IPv4 default route and the IPv6 default route. So 0.0.0.0/0 and ::/0 mean match any destination. Prevents routers from needing every internet route. Host routes define a route to one specific device, not an entire network. Here's an IPv4 host route and an IPv6 host route. IPv4 uses /32 and IPv6 uses /128 and commonly used for management or critical systems. Floating static routes act as backup routes. They only become active if the primary route fails. This is done by assigning a higher administrative distance. Here's the primary default route and the floating route. Normal static route AD equals 1. Floating route AD must be higher and used to back up static or dynamic routes. The key takeaway, static routes give you full control, predictable paths, and simple, reliable routing, but they must be manually maintained. In large enterprise networks with many subnets and remote offices, relying on static routing quickly becomes impractical. Manually configuring and maintaining routes across multiple routers is time-consuming, difficult to scale, and slow to respond to network failures. If a link goes down, static routes do not adapt. Traffic simply fails unless an administrator intervenes. Dynamic routing protocols solve this problem. Dynamic routing protocols are layer 3 protocols that allow routers to automatically discover remote networks, build and maintain routing tables, calculate the best path to a destination, and react to network changes and failures. When a route becomes unavailable, the routing protocol recalculates an alternative path and updates the routing table automatically without manual configuration. Dynamic routing protocols are grouped into different categories and subcategories based on how they operate, how they calculate routes, and how they share routing information. In the next sections, we'll explore these categories and examine how dynamic routing protocols function within a network. Dynamic routing protocols are divided into two main categories based on where they are used: interior gateway protocols, IGPs, and exterior gateway protocols, EGPs. The distinction is simple. IGPs are used inside an organization's private network, while EGPs are used between organizations on the public internet. There is only one EGP in use today: Border Gateway Protocol. BGP is used to exchange routing information between autonomous systems on the internet. An autonomous system is a collection of networks managed by a single organization, such as an internet service provider. Each AS is identified by a unique autonomous system number. ISPs use BGP to advertise the public networks they own and to learn how to reach networks owned by other ISPs. BGP selects the best route based on the path of ASNs rather than bandwidth or delay. BGP converges slowly, which makes it unsuitable for most private enterprise networks. For this reason, BGP is primarily used on the internet. eBGP is used between different ASs. IBGP is used within a single AS. IGPs are used within an organization's internal network. They are designed to converge faster and are better suited for enterprise environments. RIP is one of the oldest dynamic routing protocols and is classified as a distance vector protocol. Distance vector protocols determine routes based on distance and direction. RIP uses hop count as its metric, Bellman-Ford algorithm, and maximum hop count of 15. Because of its limitations, RIP does not scale well and is not suitable for modern enterprise networks. EIGRP is an advanced distance vector routing protocol originally developed by Cisco. It uses the diffusion update algorithm, DUAL, to calculate routes. DUAL considers several metrics: bandwidth, delay, load, reliability. By default, bandwidth and delay are used. A major advantage of EIGRP is its ability to calculate a loop-free backup route at the same time as the primary route. If the primary route fails, EIGRP can immediately install the backup route, resulting in very fast convergence. Key takeaway: EGPs are used between organizations on the internet, IGPs are used within private enterprise networks, and older protocols like RIP and EIGRP are important historically, but modern CCNA studies focus more on link state protocols, particularly OSPF, which is covered next. One of the most widely used link state routing protocols is Open Shortest Path First version 2. First defined in RFC 1247 and introduced in 1991. OSPF has become the industry standard for dynamic routing in enterprise networks. The benefits of OSPF: it's open standard, works across multi-vendor environments, scalable, supports small to very large networks using hierarchical areas, it's secure, supports MD5 and SHA authentication, it's efficient, sends updates only when a change occurs, and classless, supports VLSM and custom subnet masks. OSPF maintains three main tables: adjacency table, tracks routers that have successfully formed OSPF neighbor relationships. Link state database contains topology information for all OSPF routers in the area. And forwarding database stores the best routes calculated by OSPF. OSPF follows this sequence to reach convergence. Routers send hello packets to discover neighbors. Neighbors exchange link state advertisements. All routers build an identical LSDB. OSPF runs the shortest path first algorithm, and best routes are installed into the routing table. If a route with a lower administrative distance already exists, the OSPF route will not be installed. OSPF address is used, multicast MAC, and IPv4 multicast. OSPF packet types: Type 1 hello, Type 2 database description, Type 3 link state request, Type 4 link state update, and Type 5 link state acknowledgement. Here's the hello and dead timers. Hello timer 10 seconds and dead timer 40 seconds. Timers must match for adjacency to form. Dead timer is typically 4 times the hello timer. Here's the OSPF interface states: 1 down, 2 init, 3 two-way, 4 X start, 5 exchange, 6 loading, and finally 7 full. And you can verify with show IP OSPF neighbor. OSPF uses bandwidth to calculate cost. The default reference bandwidth, 100 megabits per second, and gigabit interfaces default to cost 1. You can adjust cost manually with IP, OSPF cost, and the value, and adjust reference bandwidth with auto cost, reference bandwidth, and the megabits per second. This must be configured on all OSPF routers. Designated router and BDR. On multi-access networks, DR manages LSA distribution. BDR is the standby, and others become druther. This reduces excessive LSA flooding, and this is the adjacency formula. Router ID selection order. So manually configured router ID, highest loopback IPv4 address, highest active IPv4 interface address. Set manually, router ID, and reset clear IP OSPF process. DR BDR Election Rules. Highest router ID becomes DR, second highest becomes BDR. Elections are non-primitive, and new routers do not trigger re-election. Here's OSPF version 2 configuration basics. Enable OSPF with router OSPF and the process ID. Advertise networks with network ID, wildcard mask, area 0. Here's an example. You can enable OSPF on specific interfaces with this command. Moving on to passive interfaces. This prevents OSPF traffic on non-OSPF interfaces. Enable OSPF on specific interfaces with this. And passive interfaces prevents OSPF traffic on non-OSPF interfaces. And that's passive interface gigabit Ethernet 0/0. Key takeaway, OSPF is fast convergent, scalable, secure, and the primary CCNA dynamic routing protocol. After configuring OSPF, it's critical to verify that routing information is being exchanged correctly and that all networks are reachable. The first step is to inspect the routing table and confirm that all remote networks are present and a default route to the internet exists, if required. You can do this with show IP route. In the branch A routing table, all remote networks are learned via OSPF, and a gateway of last resort is automatically installed. This default route was propagated from the HQ router using the default information originate command. The show IP protocols command provides high-level information about all dynamic routing protocols running on the router. From this output, you can verify OSPF is enabled on the router, the OSPF process ID is in use, the configured router ID, OSPF load balancing, and which networks the router is advertising. Additional sections of the output show passive interfaces, neighbor routers, their administrative distance, and last, update times. To confirm that OSPF adjacencies have formed correctly, use the show IP OSPF neighbor. This command displays neighbor ID, priority and state of the adjacency, dead timer countdown, neighbor IP address, and local interface used to form the adjacency. A state of full confirms successful OSPF convergence. To check OSPF behavior on a specific interface, use show IP OSPF interface. This command allows you to verify OSPF process ID and router ID, DR and BDR roles, hello and dead timer values, and number of OSPF adjacencies on the interface. For a summarized view of all OSPF enabled devices, use show IP OSPF interface brief. This output shows interface participation in OSPF, area assignment, interface IP address and subnet mask, OSPF cost, and interface state. Finally, always test connectivity between networks using a ping test. On real Cisco iOS devices, you can specify a source IP address. This confirms that routing works end-to-end and that traffic can traverse multiple OSPF routers successfully. Key takeaway, by using these verification commands, you can confirm OSPF routes are installed, validate neighbor adjacencies, identify configuration issues quickly, and ensure full network convergence. You now have the skills to configure, verify, and troubleshoot OSPF in a Cisco environment, exactly what's expected at the CCNA level. In most networks, client devices are configured with a single default gateway IP address to reach the internet. But what happens if that gateway device goes offline? If the router fails, all client traffic to external networks immediately stops. A common reaction would be to replace the failed router and reapply the configuration. While this works, it is a reactive solution that causes downtime and requires manual intervention. First Hop Redundancy Protocols provide a proactive solution. FHRP allows two physical routers to operate as a single virtual default gateway by sharing a virtual IP address and a virtual MAC address. Client devices use this virtual IP address as their default gateway and remain unaware of which physical router is actually forwarding traffic. One router operates as the active router, forwarding traffic to and from the internet. The second router operates as the standby router. If the active router fails, the standby router automatically takes over the virtual IP and MAC address and becomes the new active router. This failover happens quickly and transparently, resulting in minimal service interruption and no need to reconfigure client devices. Using FHRP greatly improves network availability and resilience, making it a best practice for enterprise networks where uptime is critical. In the next section, we'll examine the different First Hop Redundancy Protocols, their characteristics, and when to use each one. First Hop Redundancy Protocols ensure that client devices always have access to a working default gateway, even if a router fails. Cisco networks support multiple FHRPs, each with different characteristics and use cases. HSRP is a Cisco proprietary FHRP that allows multiple routers to form a single virtual router using a shared virtual IP and MAC address. HSRP router states: active, this forwards the traffic as the default gateway, and standby takes over if the active router fails. The key characteristics: default priority 100, highest priority router becomes active, preemption is disabled by default, hello timer is 3 seconds, hold timer 10 seconds, supports IPv4 and IPv6. If preemption is enabled, a higher priority router can reclaim the active role when it comes back online. So here's an example of HSRP configuration. So you have router 1, which would be the active router, and router 2, the standby router. I'm verifying HSRP with show standby brief. These commands confirm router state, virtual IP and MAC, priority and preemption status, active and standby router addresses. Failover testing shows that when the active router goes offline, the standby router seamlessly takes over without changing the client default gateway. VRRP. VRRP is a vendor-neutral FHRP that provides default gateway redundancy using a shared virtual IP address. Virtual Router Redundancy Protocol router states: master, active default gateway, and backup takes over if the master fails. The key characteristics: preemption enabled by default, default priority 100, router with the highest IP address becomes master, and VRRP version 3 supports IPv6. Here's an example of VRRP configuration. The interface gigabit 01, VRRP1 IP 192.168.11. This would be configured on both routers. I'm verifying VRRP, show VRRP brief. These commands confirm master and backup roles, virtual IP and MAC addresses, priority and preemption status. GLBP is a Cisco proprietary FHRP that provides both redundancy and load balancing. Unlike HSRP and VRRP, GLBP allows multiple routers to actively forward traffic for the same virtual gateway using a round-robin mechanism. The GLBP router states: active manages the virtual gateway, and standby takes over if the active router fails. The key characteristics: load balances traffic across routers, default priority 100, preemption disabled by default, supports IPv4 and IPv6. Here's a GLBP configuration, and this is configured on both routers. Verifying GLBP with show GLBP and show GLBP brief. These commands confirm active and standby routers, participating interfaces, virtual IP address, and load balancing status. Here's a FHRP comparison summary. Key takeaway: HSRP, simple Cisco redundancy; VRRP, vendor-neutral alternative; and GLBP, redundancy plus load balancing. You now understand how each FHRP works, how to configure them, and how to verify failover, an essential skill for building high availability enterprise networks. Summary: in this chapter, we explored how Cisco routers establish IP connectivity between remote networks. You learned how to configure and validate both static and dynamic routing, ensuring reliability end-to-end communication across an enterprise network. We also covered how to propagate a default route throughout a Cisco environment, allowing client devices to access external networks such as the internet. In addition, you gained an understanding of first hop redundancy, ensuring default gateway availability and improved network resilience. In the next chapter, we'll focus on implementing different types of NAT on Cisco routers and understanding how private networks communicate with public networks. I hope you enjoyed this video. I'm CyberEd, and I'll see you in the next one. Peace.